Welcome to Distributed Systems from Scratch. Before episode 1, there's episode 0. Think of this as the trailer, the syllabus, and the prerequisite check all in one. When you tap a button on your phone to send a message, to make a payment, to load a video, your request crosses oceans. It hits hundreds of machines. It returns in 80 milliseconds, and any one of those machines could fail at any moment. This series is about the engineering that makes that possible, the theory, the protocols, the systems, and the open problems still being solved. 22 episodes, 5 seasons, one field taught from scratch. We're going to start at the very beginning. Why do machines need to talk to each other at all? And we're going to end at the research frontier, the PhD level open problems, the papers being published this year. By the time we're done, you won't just know distributed systems, you'll know how to think in them. Here's the arc. Season 1, The Foundations. Why distributed systems exist. The two generals problem, time and clocks, the CAP theorem, and consistency models. Season 2, The Core Protocols. Paxos, Raft, Replication, Sharding, Fault Tolerance, Transactions, Gossip, every algorithm that runs the modern internet. Season 3, Building, Real Storage, Engines, Streaming Systems, Design Patterns. Season 4, Advanced CRDTs, Geo-Replication, Byzantine Fault Tolerance. And Season 5, Research, TLA plus Formal Verification, Distributed Machine Learning at GPT scale, 9 open problems, and how to enter the research world yourself. By the end, you will understand 4 layers of this field. The theory, CAP, FLP, impossibility, linearizability, happens before, why consensus is fundamentally hard. The protocols, Paxos, Raft, two-phase commit, Sagas, Gossip, PBFT, hot stuff. The systems, GFS, Bigtable, Cassandra, Kafka, Spanner, CockroachDB, the CRDT systems behind Figma, the training infrastructure behind GPT, and the frontier, TLA plus the way AWS uses it, 3D parallelism for trillion parameter models, and the research problems still wide open. Who is this for? If you're a back-end engineer wanting to build at scale, yes. If you're a new grad prepping for system design interviews, yes. If you're a self-taught developer tired of fragmented blog posts, especially yes. And if you're considering a PhD, this series is your runway. What you need to bring: comfort writing code in any one language, basic familiarity with the web, and patience. Distributed systems reward depth, not speed. But first, there are 5 things this series will not teach you. 5 prerequisites. If you don't have them yet, fix that first. Because episode 1 assumes them, and every episode after that builds on them. Let's go through all 5. Here they are. Networking, TCP, IP, DNS, latency versus bandwidth. Operating systems, processes, threads, IPC, virtual memory, concurrency, locks, races, atomics, memory models, database internals, B trees, write ahead logs, MVCC, ACID, and algorithms, graphs, hashing, Bloom filters, Big O. About 6 weeks of focused study if you're starting cold. A lot less if you're mid-career and just need a refresher. We'll go one by one. Prerequisite 1, computer networking. Distributed systems live on networks, and the network is not free, not reliable, and not fast. If you don't internalize that, nothing else in this series will land. What do you actually need? On the concept side, the OSI and TCP IP layers, the TCP three-way handshake, the difference between TCP and UDP, how DNS resolution works, the differences between HTTP 1.1, 2, and 3, and the cost of TLS handshakes. On the mental model side, and this matters more, latency is not bandwidth. Bandwidth is the width of the pipe. Latency is the distance light travels. Memorize the latency numbers. L1 cache half a nanosecond, RAM 100, SSD 100 microseconds, network half a millisecond to 150, and read The Eight Fallacies of Distributed Computing, Peter Deutsch, 1994. Every assumption in there breaks in production. The Brush-Up Plan, Computer Networking, a Top-Down Approach by Kurose and Ross. The undergrad standard, skim chapters 1 through 3 and chapter 6. High Performance Browser Networking by Ilya Grigorik, free online. The best practical book on TCP, TLS, and HTTP. The paper to read, End-to-End Arguments in System Design, Sulzer, Reed and Clark, 1984, and then write a TCP echo server, Beach's Guide. The intuition is in the code. Prerequisite 2, Operating Systems. Every node in a distributed system is an OS process. Understand the unit before you compose them. The concepts, processes versus threads, what context switching actually costs, how schedulers work, virtual memory and paging, system calls, and inter-process communication. The mental models that matter most, kernel space versus user space, and why every syscall is expensive. The page cache, why a lot of what you call disk I/O is actually RAM I/O, async I/O, EPOL on Linux, KQ on BSD, I/O urine as the modern replacement, and why event loops exist. File descriptors, sockets, files, pipes, all the same thing. And containers, they are not virtual machines. They are C groups and namespaces, two Linux features. That's it. Operating Systems, 3 Easy Pieces by the Arpacid Source, free online, the clearest OS textbook ever written. Read parts 1 and 2, The Linux Programming Interface by Michael Karisk for syscall reference. And then build a tiny shell in C fork, exec, wait, pipe. You will never forget how processes work. Bonus, run strace on alias, on curl, on redis CLI. Watch the syscall layer happen in real time. Prerequisite 3, Concurrency and Parallelism. Distributed systems are concurrent across machines. And here's the rule. Get concurrency wrong on one machine, and you will get it catastrophically wrong on 1,000. The concepts, race conditions, mutexes, semaphores, reader-writer locks, deadlock, live lock, atomic operations, compare and swap, and the ABA problem. The mental models, memory ordering, sequential consistency, acquire, release, relaxed, cache coherence and false sharing, happens before. The foundation of every consistency model we'll discuss in this series. Reentrancy and thread safety are different things. Lock-free is not the same as wait-free. And important, async await is cooperative scheduling, not parallelism. They are not the same thing. The art of multiprocessor programming, Hurley High and Shavit, the classic. Read the chapters on locks, atomics, and lock-free queues. Java Concurrency in Practice by Brian Getz. Even if you never write a line of Java, the patterns are universal. The paper, Lamport, 1974. A new solution of Dijkstra's concurrent programming problem. The bakery algorithm. Tiny and beautiful. Then code it. A thread-safe counter, a lock-free queue, a reader-writer lock. In that order. Prerequisite 4. Database internals, storage engines, transactions, isolation levels. This is the vocabulary you will use to discuss every distributed data system in this entire series. Concepts, B plus trees and how relational databases index, LSM trees and how Cassandra, RocksDB, and LevelDB store. Write-ahead logs, durability before mutation, the core idea behind every crash-safe database. MVCC, multi-version concurrency control, where readers don't block writers. ACID, and query execution, plans, joins, indexes. Then isolation levels, read uncommitted, read committed, Postgres default, repeatable read, MySQL InnoDB default, snapshot isolation, spanner, CockroachDB, and serializable. The strongest, the most expensive. And the anomalies each one allows. Dirty reads, lost updates, write skew, phantoms. You need this language fluently. Database Internals by Alex Petrov, the single best book on storage engines and replication. Read part 1 before episode 1. Designing Data Intensive Applications by Martin Klipman, DDIA, chapters 3, 7, and 9. The papers, Jim Gray, The Transaction Concept, 1981. Then Mohan and colleagues, Aries, 1992, and the course, CMU 15445, Andy Pavlo. Free lectures, possibly the best database course on the internet. Prerequisite 5, Algorithms and Data Structures, the building blocks. You won't reinvent quicksort, but you'll see Bloom filters, Merkle trees, and consistent hashing everywhere in the next 22 episodes. The foundations, read Big O fluently, hash tables, binary search and its variants, heaps, graph traversal, BFS, DFS, topological sort, sorting and merging, and external sort, which actually matters at scale. Then the specialized stuff, Bloom filters used in Cassandra, used in Bigtable, used to skip discretes. Hyperlog counting unique items in a stream with kilobytes of memory. Skip lists, Redis, LevelDB, Merkle trees, anti-entropy, Git, blockchains, consistent hashing, Dynamo, every CDN, and count min sketch, streaming heavy hitter detection. These are not exotic. They are everyday tools in this field. CLRS, Introduction to Algorithms, is a reference, not a read through. Look things up. Designing Data Intensive Applications. Chapter 3, Bloom filters, hash indexes, LSM, and B trees in one chapter. The paper, Karger and colleagues, 1997. Consistent hashing and random trees. The paper behind every modern partitioning scheme. Then code three things: a Bloom filter, consistent hashing, and a Merkle tree, about 200 lines each. You will read every later chapter of this series differently. Self assessment, 5 questions. Networking. Can you explain why a TCP connection from Frankfurt to Singapore takes about 150 milliseconds minimum, regardless of bandwidth? OS. Can you describe step by step what happens when your program calls read on a file? Concurrency. Can you write a thread safe counter and explain why counter plus plus by itself isn't? Databases. Can you explain the difference between read committed and repeatable read and give an anomaly each one allows? Algorithms. Can you explain how a Bloom filter trades space for false positives and why it has 0 false negatives? 5 yes answers. You are ready for episode 1. Anything else? Spend a week on that prereq first. There's no rush. 5 rules of the road. Watch in order. Each episode builds on the previous. Don't skip season 1 to get to Raft. Pause and code. After episodes 6, 7, 9, and 13, implement a protocol. MIT 65840 labs are free, public, and excellent. Read the original paper for every system mentioned. Episode 22 teaches the 3-pass method for reading papers efficiently. Discuss. Find one other person learning this. Explain Paxos to them. You will discover the gaps in your understanding. And finally, build something real: a toy KV store, a chat server, a distributed log service. Theory becomes intuition only through code. Ready? Episode 1 starts now. 22 episodes, 5 seasons, from scratch to the research frontier. Subscribe, like, share, and most importantly, build something. I'll see you in episode 1.